Welcome to Math 104, Section 7.3, Simplifying Radicals. I'd like everybody to start by comparing the results of evaluating those two expressions. So if you evaluate these individually, square root of 4 is 2, square root of 25 is 5. Multiply them out and we get 10. Now here, we're going to simplify underneath the radical first. So that turns into the square root of 4 times 25, which is 100. Take the square root, and we get 10. So we get the same answer either way. And that's the idea behind the product rule for radicals. We can either evaluate the two radicals individually and then multiply them, or we can multiply the numbers together and then evaluate the radical. You get the same answer either way. So this is a very important property we'll be using. We'll use the transform equations. We can use them going either direction. So for this one, we want to simplify, so we're going to go to the right, from two separate radicals to one. So this ends up being 3 times 7 underneath the radical, which is the square root of 21. For the second one, we're going to multiply 7x squared times 13x. So we get the fourth root of 7x squared times 13x. Then multiplying it out, we get the fourth root of 91x to the third power. Now this one, notice that we have different indices there. We have a 3 and a 4. Product rule for radicals only works if we have the same index. So this one cannot be simplified. Your turn, number 1. Multiplying that out, we get the square root of 55. Now the second one, we've got 3 and 7 for our indices, so we cannot simplify that one. But this one, we have the same index, so we can. So this ends up being the fifth root of 3x times 5x to the third, which is the fifth root of 15x to the fourth. All right, next up, I'd like to compare the results of evaluating those two expressions. Square root of 144 is 12. Square root of 36 is 6. Then we can divide to get 2. Now here, 144 divided by 36 is 4, so that turns into the square root of 4, which is 2. So same answer either way, and that's the idea behind the quotient rule for radicals. Right? We can take two numbers, divide it underneath a radical, and then split it up into two different radicals, evaluate those individually, and then divide. We get the same answer. So that's going to be a very useful property, especially for evaluating things like this. We can't divide 100 divided by 81 and get a whole number, so let's split it up. So that gives us the square root of 100 divided by the square root of 81. Square root of 100 is 10. Square root of 81 is 9. So that gives us 10 ninths. B. We're going to split this up. We get the fourth root of 35 over the fourth root of 81. Now the fourth root of 35 cannot be simplified, so we're going to leave that in the numerator. And then in the denominator, we got the fourth root of 81, which we can simplify down to 3. So fourth root of 35 over 3. Next up, we'll split this up. We get the square root of x squared over the square root of 9. All right, evaluate those individually. And now we're going to simplify this. Remember that we have the same index as we have the exponent, and they're even. We have the absolute value of x. And here we get the square root of 9, which is 3. Your turn, number 2. All right, splitting that up, we get the square root of 36 over the square root of 49, which is 6/7. Now, the third root of 41 cannot be simplified, so we'll leave that in the numerator. And the third root of 64 is 4. So third root of 41 over 4. All right, splitting that up using the quotient rule for radicals. Now we have an odd exponent and odd index that match. So that is reduces to x. All right, we don't need the absolute value when we have odd values there. All right, here, third root of 8 is 2. So x over 2 for that one. Next up, we're going to be simplifying radicals. And we've got 4 criteria for a simplified radical. First one, the radicand, that's the expression underneath the radical, has no factor raised to a power greater than or equal to the index. All right, so we can break up 72, and we're taking the square root. So what we want to do is be able to factor 72 into something times a perfect square. And so since we're taking the square root, the perfect square and the square root, we'll be able to evaluate that into a whole number. Okay, so the square root, it's a factor of 72, is 36. So this can be written as 36 times 2. All right, now we can use the product rule to break that up into 2 separate radicals. Square root of 36 times the square root of 2. All right, now we have square root of 36, which values to 6, and we get 6 square roots of 2. Your turn, number 3. All right, so 48 has a factor that is a perfect square, and that is 16. That's the largest one. There are others, there's 4 as well, but 16 is the largest one. So we got 16 times 3. We use the product rule to break it up into the square root of 16 times the square root of 3. And that simplifies to 4 square roots of 3. Next up, we're going to look at a radical with an index of 3. So now we're looking for perfect cubes. So we want to break this up into something times a perfect cube. So that is 64 times 3. 64 is the largest perfect cube. It's a factor of 192. And we can use the product rule to break this up into the third root of 64 times the third root of 3 Third root of 64 is 4, so we get 4 times the third root of 3. Your turn, number 4. Third root of 54. Now 54 we can break up into 27 times 2, 27 being a perfect cube. Now use the product rule to break it up into 2 separate radicals. And make sure when you're doing this, you're always keeping the same index. Never change the index. I see a lot of students will start off with the third root. As soon as they start using the properties, they just leave it off and start writing square roots. All right, evaluating, we get the 3 times the third root of 2. All right, now let's try one with an index of 4. All right, so we've got fourth root of 243. So now we want perfect quads. Not a technical math term, just, there you go, squares, cubes, what are we going to call them? I call them quads. Summed into the 4th power. So we can break this up into the 4th root of 81 times 3. And use the product rule. 81 and 3. 4th root of 81 is 3, so we get 3 times the 4th root of 3. Your turn, number 5. So in this case, we want a perfect quad, and that is 16. 80 breaks up into 16 times 5. Now use the product rule to break it up into 2 separate radicals. Evaluate this one is 2, so we get 2 times the 4th root of 5. All right, now we're going to simplify radicals involving variables. Now the best situation arises when the exponent is a multiple of the index. Let's take a look at the square root of x to the 8th power. Now early in the course, when we were simplifying expressions like this, we would take the exponent and divide it by 2. Well, let's see why. Now let's write this in rational exponent form. 8 is the exponent, 2 is the index on the radical, so we write that as x to the 8 over 2, and that's why we divide by 2. So dividing it out, we get x to the 4th power. Your turn, number 6. Convert to rational exponent form. Index is 2, so that goes on the bottom. 6 goes on top. Divide it out, and we get x to the 3rd power. Now, not always will they work out nicely like that. Square root of x to the 7th power. All right, now go back to requirement number 1. What I read before, the radicand has no factor raised to a power greater than or equal to the index. Well, 7 is greater than or equal to the index, which is 2. All right, so what we're going to do is just like over here, we wanted to break up into, when we did square roots, perfect squares. When we did third roots, perfect cubes. And here, perfect quads. Here we have a square root, so we want to find something that's a perfect square. And we want the largest perfect square. perfect squares are exponentials with even exponent. So that means we want the largest even exponent less than or equal to 7, and that's 6. So we're going to break this up into the square root of x to the 6th times x. Now we can break it up using the product rule. So we get the square root of x to the 6th times the square root of x. Now, why do we want an even exponent here? Because when we convert this to rational exponent form, we're going to get an even division there that gives us a whole number. So we got x to the 6 over 2 times the square root of x. And x to the 6 halves is x to the 3rd. So we get x to the 3rd times the square root of x. And that is fully simplified because now the exponent on the x is less than the index, 1 being less than 2. Your turn, number 7. All right, break it up so that we have the largest even exponent that's less than or equal to 9. Okay, so that is 8. So that's going to be square root of x to the 8th times the square root of x. And convert this to rational exponent form. 8 over 2 is 4. So that gives us x to the 4th times the square root of x. Now if we have more than one variable, we'll just do each variable separately. And so we're going to write to the product rule, breaking this up into 4th root of x to the 24th power times the 4th root of y to the 20th power. Now we can convert to rational exponent, so that is x to the 24 over 4 times y to the 20 over 4. And that equals x to the 6th, y to the 5th. Your turn, number 8. Product rule breaks it up into 2. Now convert to rational exponent form. All right, we got the exponents, the numerator, index is the denominator, and then divide them out, and we get x to the 7th, y to the 3rd. Now some of these are going to have variables with coefficients. So we'll just do those separately as well, requiring both techniques that we've seen before. So we're going to do the 3rd root of 16 x to the 14th power. All right, so when we split this up, we want to split up into 2 different radicals. One radical contains all of the perfect cubes, and then the other radical contains the leftovers. So 16 can be broken up into 2 times 8, with 8 being a perfect cube, and x to the 14th can be broken up into x to the 12th times x squared. All right, now we have 12, which is the largest multiple of 3 that's less than or equal to 14. So like over here, we were looking for the largest even number. Largest even number that is less than or equal to 9. Now since we're taking, our index is 3, this is the 3rd root, we want the largest number that's a multiple of 3 that's less than 14, less than or equal to. All right, so we have a perfect cube here and a perfect cube here. So we're going to separate those off into one radical. I usually write that as the first radical. So we got third root of 8 x to the 12th power times the third root of all the leftovers now, so 2 and x squared. Now this one can be simplified and that one's done. So over here, third root of 8, technically what we should do is split this up. So that we go the third root of 8 times the third root of x to the 12th power, and then do each of them individually. Oftentimes this step is skipped, and that's fine with me if you want to skip this one. All right, now we'll evaluate each of these. Third root of 8 is 2. Third root of x to the 12th, that'd be in rational exponent form, that's 12 divided by 3, which is 4, so x to the 4th power. And then the leftovers stay inside the radical, 2x squared. Now, 2 does not have any factors that are perfect cubes, and x squared, the exponent, is less than the index, so that is fully simplified. Your turn, number 9. All right, we got third root, so we're going to look for perfect cubes that are factors of 81. 81 can split up into 27 times 3. We got the third root, 27 times 3. There's our perfect cube. And x to the 8th, now we want the largest multiple of 3 that's less than or equal to 8. So 3, 6. So that's x to the 6th times x squared. All right, now we'll break this up into, first radical contains all the perfect cubes, so that's 27x to the 6th. And the second radical contains the leftovers, 3x squared. Evaluating this, third root of 27 is 3. Third root of x to the 6th is x squared. 6 divided by 3 to get x squared. And then this radical stays just as it is. Third root of 3x squared. All right, next up. We're simplifying negative fourth root of 81, x to the 17th, and y to the 11th. All right, now we have 3 things to think about here. You think about 81. And as it turns out, 81 is a perfect quad. So that's going to go into the first radical containing all the perfect quads. All right, now we want the largest multiple of 4 that's less than or equal to 17. So just count by 4s, 4, 6, or 4, 8, 12, 16. So 16 is the largest multiple of 4 less than 17. So we write x to the 16th power. Largest multiple of 4 that's less than or equal to 11 is 8. So we'll put y to the 8th power in the first radical. Second radical contains all of the leftovers. So we have 16 of the 17 x's here, leaving 1 over here. And we have 8 of the 11 y's in this one, so we'll need 3 y's left over in that one. Alright, so this one's done. Both of the exponents are less than the index, so that one's fine. And over here we can simplify. Remember, don't forget your negative out front. 4th root of 81 is 3. 4th root of x to the 16th power, take 16 divided by 4 to get x to the 4th. Y to the 8th, take 8 divided by 4 to get 2, so that is y squared. And then this remains just as it is, 4th root of x, y to the 3rd power. Your turn, number 10. So we're taking the 4th root, or the negative 4th root of 16, x to the 10th, y to the 19th. Now 16 is already a perfect quad, so that is going to go directly into the first radical. Now we need greatest multiple of 4 that's less than or equal to 10, that is 8. So I'll have x to the 8th over here. And now we need greatest multiple of 4 less than or equal to 19, that is 16, so y to the 16th power. And then over here, we got the 4th root of the leftovers. We have 2 more x's unaccounted for, so we'll put them over here. And here we have 3 9s left over, so we'll put them here. Now we can evaluate this one. So we get negative, 4th root of 16 is 2. 4th root of x to the 8th, 8 divided by 4 is 2, so we get x squared. And 16 divided by 4 is 4, so we get y to the 4th power. Times the 4th root of x squared, y to the 3rd. Now, next example requires a little bit of analysis to see what's going on here. Always be very wary when you see a negative underneath the radical. So in order to evaluate that, we're going to need to have, usually we're going to need an odd index, or we'll need something going on with this x. It's different than what we have here because x to the 8th power, sorry if you can't read that, x to the 8th power is always going to be an even number. Sorry, it's always going to be a positive number, not an even number. So if we have a positive number here and we multiply it by a negative number, we're guaranteed to get a negative number. You cannot take the square root of a negative number and get a real number. So this is not a real number. Now we'll see later on how to handle those, but right now we're just going to leave it at that. Simplifying radicals using lesser indices. Put it down here. So let's say, for example, we've got the 12th root of 3 to the 9th power. All right, so we're going to want to reduce this. Now let's look back at our requirements here. This is an example of the requirement number 4. Exponents in the radicand and the index of the radical have a greatest common factor of 1. All right, exponents in the radical and the index have a GCF of 1. That is not true here. 9 and 12 have a GCF of 3. So You have to do something here. Let's convert this to rational exponent form. So that would be 3 to the 9/12. And now that fraction can be simplified. So we're going to write that as 3 to the 3/4. Okay, now we want to express the answer back in radical form. So we're going to convert this back to radical form. The reason we wanted to convert to rational exponent form is so we can reduce that fraction. Now when we convert back, remember 3 is still the exponent and 4 is the index. So we're going to do 4th root of 3 to the 3rd power when we convert back. And now we can evaluate 3 to the 3rd, which is 27, so we got the 4th root of 27. Your turn, number 11. You got the 15th root of 4 to the 10th power. So converting to rational exponent form, that is 4 10/15. Now we can reduce the fraction. That turns into 4 to the 2/3 power. Now we can convert back to radical form. So 3 is the index, and 2 is the exponent. So 3rd root of 4 squared, which is the 3rd root of 16. Now let's try this with a variable in there. All right, the 10th root of x to the 8th power. All right. Convert to rational exponent form. That is 10 to the 8/10, x to the 8/10 power. Now we can reduce this fraction to x to the 4/5 power. And now we can convert back to radical form. 5 is the index. And x to the 4th power. 5th root of x to the 4th. Your turn, number 12. We're going to do the 12th root of x to the 6th. All right, that's x to the 6/12. Reduce that fraction to 1/2. And a 1/2 exponent means the square root of x. Right? 2 becomes the index. We don't write it because that's implied. So we have a square root. And x is to the 1st power, and we don't write that one either. That one's implied as well. So square root of x. Now all these, when we got back into a radical form, they were already pre-simplified. That won't always be the case. So next example is the 6th root of x to the 21st power. So that is x to the 21/6. Now we'll reduce this. That gives us x to the 7/2, which is the square root of x to the 7th power. All right, 2 is the index, and 7 is the power. All right, now this can be simplified because we can break this up into x to the 6th, square root of x to the 6th times the square root of x. All right, 6 is the largest multiple of 2, less than or equal to 7. And now x to the 6/2, if you wrote this in fractional exponent form, 6 divided by 2 is 3. So that's x to the 3rd power times the square root of x. Your turn, number 13. Ninth root of x to the 24th power. So 24 ninths, if we divide the top and bottom by 3, we get 8/3. So there's the reduced form. Now we'll go back to radical form, which is third root of x to the 8th. All right, largest multiple of 3 plus less than or equal to 8 is 6. So we'll break this up into the third root of 6, or x to the 6th, times the third root of x squared. All right, 6 divided by 3 is 2, so we have x squared there. And then we have the third root of x squared. X squared times the third root of x squared. Now, one nice thing about being able to change forms is that it allows us to do things we couldn't do otherwise, such as multiplying radicals with different indices. Right? The power rule, or the product rule, only applies to radicals with the same index. So we cannot multiply together radicals with different indices. But we're going to use a technique that allows us to do so. So we're going to take the 8th root of 3 and multiply by the 4th root of 5. Different indices, so we can't do anything with those until we convert them. We're going to convert to rational exponent form. All right, so now we have 3 to the 1/8 times 5 to the 1/4. All right, now we're going to convert these such that we have a common denominator. All right, least common multiple of 4 and 8 is 8. So 8's the denominator we want. So we're going to rewrite this one with an 8 denominator. So it'll be 2 8ths. So that gives us 3 to the 1/8 times 5 to the 2 8ths. Right, now we have a common denominator, so now we're going to convert back to radical form. So that is the 8th root of 3 times the 8th root of 5 squared. Now we have the same index. Now we can use the product rule. So now we're going to do the reverse of what we've been doing. Before we were taking numbers and splitting them up into 2 separate radicals. The great thing about the product rule is that it works in both directions. So now I'm going to take these and combine them, all underneath one radical. 8th root of 3 times 5 squared. All right, 5 squared is 25 times 3 is 75. So this equals the 8th root of 75. And there is your fully simplified form. Your turn, number 14. So we'll convert to rational exponents. That's 2 to the 1/6 power times 4 to the 1/3 power. Now we want a common denominator with the fractions. So I'm going to go for a denominator of 6. So can change this to 2/6. So that'd be 2 to the 1/6 times 4 to the 2/6. All right, now we're back to radical form. So we have the 6th root of 2 times the 6th root of 4 squared. So at this point, you should have a common index. If not, go back and check your work. Now we will use the product rule. So 2 times 4 squared underneath the radical. We'll evaluate this. 4 squared is 16 times 2 is 32. So the 6th root of 32. Next up, we've got the 4th root of 8 times the 3rd root of 6. Okay, so that is 8 to the 1/4 power times 6 to the 1/3 power. Now to get a common denominator, find the least common multiple of 4 and 3, and that's 12. So we'll convert these fractions to have a denominator of 12. So 8 to the 3/12 times 6 to the 4/12. Now we're back to radical form. 12th root of 8 to the 3rd power. And over here we got the 12th root of 6 to the 4th power. Now we use the product rule. Combine it all under one radical, and that gives us the 12th root of a very large number, 663,552. Your turn, number 15. We got the square root of 5 times the 3rd root of 4. All right, so this can be written as 5 to the 1/2 power, right? Implied exponent of 1 and an implied index of 2. So 5 to the 1/2 times 4 to the 1/3. Now our common denominator here will be 6. So we're going to change this to 5 to the 3/6 power times 4 to the 2/6 power. Now let's go back to radical form. Now we have an index of 6. So 6 root of 5 to the 3rd power times the 6th root of 4 squared. So that gives us the 6th root of 5 to the 3rd times 4 squared. All right, so that's 125 times 16, which gives us the 6th root of 2,000. And there's your fully simplified form. Now, when we're doing operations later on in this chapter, once we get an answer, it's always going to be required to simplify the result. So this is going to be a very important skill going forward in this chapter. So make sure you master this one before moving on.